Hi, linear algebra students. So this next series of video covers a whole topic, which is the distance between skew lines. It's going to contain two videos. One of them being this one is the explanation. So how do we actually find the distance between skew lines? And the second video will be a particular example with that process being applied. Okay, so let's get to it. And by the way, these are both mandatory, okay? You need this for your exam. So again, fill in your notes, make sure that you understand this part. So, reminder, two lines in our tree are skew if they don't intersect, but are also not parallel. So if I can form them with my arms, they would look somehow like this, right? So they are not like this, they are not parallel, but they also don't intersect, like there's a space in between, they don't touch, okay? And this is only possible in R3 and higher dimension. It's totally not impossible. It's totally impossible in R2. So that's why you haven't seen this concept before this course. And okay, now we would like to find the distance between these two lines, where in my case, the distance is probably just this, right? Where you translate one a little bit like perpendicular to the other, if that makes sense, actually, because this is the process. This is how you will find it. So that's what we want to do. We want to find the distance between two skew lines, L1 and L2. And you don't need to translate them perpendicularly, right? You can translate them in any kind of way, and the process will work. Okay? The only thing you're not allowed to do is to actually bend them. Okay, so here it is. Uh, this is the picture of two skew lines where I put some words here to help your imagination, but still it does require some kind of spatial understanding. So I wrote here that L2 is at the bottom and L1 at the top. So you have to imagine them like this, okay? So this is L1, this is L2. And it's basically has three steps. So the first step is to take the line that's at the top and drop it on L2. Okay, so you basically just do this. Okay, and what's gonna happen is that as they intersect, there's gonna be a plane that there's gonna be a single plane actually that contains them both. Okay, so call this plane P1. Then what you're going to do is you're going to do the exact same thing, but in reverse. In other words, instead of moving the first one down like this, you're going to move the second one up. Okay? So it's going to create another plane. That's it. It's going to create another plane. That is this one, P2. Okay? Now here's the key part of the process. The way you translate the line, sorry, is important because you want to translate them in a way that you're changing the position vector, but not the direction vector. So that's what I was telling, right? You translate it like this, but not like this, right? In other words, you translate them in a way that the direction vector of both lines remain the same. If you do that, it means that the two planes will be parallel, okay? And them two planes being parallel reduces the problem into a problem that we already know how to solve. We want to just find the distance between the two parallel planes. Okay, so now let's write the step-by-step process. Okay, so all right, let's actually perform another drawing, which now I will redo pretty much the same drawing. So like that's it. This will be L1 at the top, and we will draw L2 at the bottom. So L1 top, okay, and L2 bottom. Okay. So how is it going to work? The first step is to create a vector Q from L1 to L2 or vice versa, right? So maybe it wasn't a good choice to put L1 at the top, but it's okay, right? You're just going to create a vector Q. And what is that vector Q? It's going to be, well, actually, you can take a point on the second line or let's say a point on the first line and subtract the point on the second line, right? So this will create the vector that's right here. It will be P1 minus P2. So remember that these are position vectors on both lines. So position vectors of their respective lines. Okay, now remember, and actually I'm gonna resketch, let's say, the plane number 1, okay, just so that it makes sense. So if you drop this line onto L2, okay, so you get, and actually, okay, let's resketch this entire thing. So okay, you have like L1, then you have L2, okay, and then remember what I did was that I dropped this L1 on L2. Not guaranteed that this is the shortest distance, but let's suppose that it is, okay? So just to make the idea a little bit clearer, okay? Then what you're gonna do is this vector Q, that let's redraw it. Let's suppose that it was over there actually, okay? Let's suppose that we were just lucky and that it was over there, okay? That being said, as I said, it doesn't make any difference. What you're gonna do is you're gonna project it on the normal vector of the plane P1, okay? So, okay, we have here, and now I'm gonna change its color. I'm gonna write this as being the plane. Yeah, this right here will be the plane P1, okay? So what you wanna do is you wanna find the normal vector of that plane. And this is where the cross product will come into play because both lines have a direction vector. So this line, let's say, has a direction vector V2. And don't forget that as we translate line number 1, we want to make sure that we don't change the direction vector, which means that step number 2 is to really just find the normal vector by cross-producting V1 and V2. So it's going to be V1 cross V2. Now this is going to produce a normal vector, and let's say that the normal vector is really, really tiny, okay? Suppose. Normal vector could be like this, okay? Then what we want to do is we want to project the vector Q on that normal vector. So this will be step number 3. Let's color code that in black. Okay. So we want to compute the projection of Q on N. Okay. And let's write down so this is the formula, Q on N. And now remember that this is the dot product of N and Q divided by the norm of N squared multiplied with N. Okay, and it will give pretty much like this vector right here. So unfortunately I'm crowding my diagram, but it will give this vector. Okay, so the black vector that actually reaches the line number 1. Okay, and of course step number 4 is to take its norm, right? So we just take the norm of the resulting projection vector. And now something I want to say is you might remember in one of my other videos, which was actually optional. You can actually just say that the norm will be n dot q. Is that it? N dot q over. Oh yeah, it's a good idea actually. So let's compute the norm of this vector. So we have n dot q divided by n squared, okay, multiplied by times the vector n. Okay, so the reason I do this is because you can easily simplify this. So this will give you And unfortunately, I don't have space, so I will write it right here. It's going to be the absolute value of the norm of n and q divided by the norm of n. Okay, so you can work this out. You will see that this is how it simplifies. Otherwise, just take the projection and compute its norm. That's what I would do actually. All right, I hope this video was helpful. A lot of colorful drawings. So see you in the next video, which we're going to take a specific example and we're going to compute the distance between two very specific skew lines. See you there.